Hello. Now, today we are going to be talking about something called p-values, which is just another way of effectively dealing with a hypothesis test for a mean of a sample. They are very, very closely connected ideas. From a real-world perspective, the reason why p-values exist is that when you're doing more advanced statistical analysis than we do in Leaving Cert, it turns out that p-values are a more useful way to understand the probabilities of things, of the how likely or unlikely an experiment is to have been pure chance. From our perspective, it's simply a requirement to know how to deal with a hypothesis test for a mean of a sample in a different way than we have already talked about. So the way that this works, I'm going to come to what the word p-value means in just a second, but to begin with, we know that we have our 95% confidence interval. It's between minus 1.96 and plus 1.96 in terms of a z-score. And that is how we usually test our hypothesis test for our sample mean. However, implied in that is that there is an area, there is a range outside of this where 5% of our overall population is, our overall distribution is. So what we do is, you can see this area that I have colored in blue. This is 5% of the area underneath the curve. So if we are inside the, let me just turn this blue. If we are inside the 95% confidence interval, and we have a particular z-score, I'm going to put it as z here, the area, and that would be minus z here, so the area less than z, minus z, and greater than plus z, in this case would be larger than 5% of our overall distribution, because you can see the 5% area that I have colored in already, and that this area I've marked would be bigger than that, would be a larger area. So, and likewise with my example that I have drawn down here, you can see that these two graphs are supposed to be very similar. So this would be, we'll say, the 95% confidence interval. This would be my minus 1.96. This would be my plus 1.96. And the area in blue in this one is smaller than 5%. So we would say that we were outside of our 95% confidence interval. So we're going to do a question to make this more concrete, but that's the general introduction. So if the area above and below plus z and minus z is less than 5%, or you'll get a decimal, so 0.05, we are outside of the 95% confidence interval, and we would reject our null hypothesis. We'd reject H0 as we usually would if we were outside of our 95% confidence interval. Now, this blue area that I've been referring to here has a formula for it, or rather, that blue area that we've been talking about is called the p-value for the particular value of z, for the particular sample statistic we're talking about. And the p-value is the area of our two blue areas here, and it's going to be the probability of z being greater than, 2 times the probability of z being greater than the modulus of our particular z-score. So we're going to get a particular z-score, and then we're going to look for the probability of z being greater than that number, and we're going to double it, because this part here gives us the probability of z being greater than z here, and we want to double it because we want the same area down beyond minus z. So this formula you are unfortunately required to know by heart. You have to know this formula by heart. It is not in the log tables. They do not give it to you in the exam. You have to know that that is the formula for a p-value. Now, let's get into a question to make this a little bit more concrete. So we're looking at page 345, question 9. Bottom of the page. Standard batteries have a mean lifetime of 85 hours with a standard deviation of 12 hours. A sample of 200 long life batteries has a mean lifetime of 86.5 hours. Now, in the questions in the book, they break this down into get your sample statistic, work out your p-value, and then do your hypothesis test. In the exam, they aren't required to do that, so I'm just going to go through the steps that you would use given the information in question 9 for an exam style question. So based on question 9, what's the first thing we do? If we don't know anything about what we're doing, we're still going to write down the information given to us in the question. So we're told that we have a population of batteries, of our standard batteries, which have a mean lifetime of 85 hours. So mu, our population mean, is 85 hours. The standard deviation of our population is 12 hours. We have a sample of size 200. Again, this is greater than 30, so we are going to be able to make our normal distribution assumption. And our sample mean from our 200 batteries is 86.5 hours. Be careful of your units. All of this is in hours. They could have told you 86 hours and 30 minutes and required you to change that into just hours. They're relatively unlikely to do that in a statistics question because they already have so many steps, but always be careful with the units that they give you in a question and write out your information clearly. Now that's what we're given in the question, and we're asked to get the p-value. So we're going to say that we're just asked for the p-value. Now, we're going to set this up the same way as we usually do. We're going to, part 1, set up our null hypothesis, and that is going to be that the mean is still 85 hours. And what's the alternative? It's just not that. Sorry, that should be a colon, not an equal sign. Colon. The mean is not 85 hours is the alternative hypothesis. So sometimes it can get confusing as to how to construct a null hypothesis and alternative hypothesis. If you state it mathematically, it's very straightforward. If your assumption is your mean is 85 hours, then the opposite of that is just that your mean is not 85 hours. Now, that's our step 1, as it always is in our hypothesis test. Step 2 is going to be getting our test statistic. That is something like that. And remember that that really just means our z-score that we know the formula for. Always write down your formula. This is in your log tables. This is the formula that's actually listed under hypothesis testing, helpfully enough, on page 35 in your log tables. If we sub all of that in, we get 86.5 minus 85 all over sigma is 12 all over the square root of n is 200. Throw all that in our calculator and we get 1.7678. This is a z-score, so we are going to say that z is approximately equal to, remember our z-scores only go to 2 decimal places in our log table, so there's no point in going beyond that, so we get our z-score of 1.77. That's our step 2. Now, remember we've got a z-score here, which is, we'll say our z up here, and we are looking for the area of our under our curve that is above that, and we are going to double that. That's our p-value, and that is step 3. for a p-value, we are going to write down our formula. So 2 times probability of z being greater than the z-score that we got, 1.77. The reason for the absolute value is so that we don't get thrown. So we don't get thrown if this is a minus. Obviously, you could have, if our sample mean was lower than our population mean, we would have gotten a negative number for our z-score. But to keep the maths consistent, we're always going to take being above the positive value of z, the positive version of z. That's why we have our absolute value lines in our formula. So be careful that you don't forget that you have an absolute value there. You're always going to take the positive. Now, we recognize that we don't have our statistics table doesn't give us z above a particular value. It gives us z below. So we're going to have to do our method of recognizing that we could do 1 minus z less than this number. So equals 2. I'm going to draw it as a picture because that's how I tend to do things. Z is 1.77 and we're looking for the area above that. Oops. Which means we are looking for 2 times 1 minus the area below that. Translating that into maths, we have 2 on 1 minus. We read this from our tables, so open up page 36 and 37 in your tables, and we're looking for probability of z less than 1.77. So you go to 1.7 on your left-hand side table, and then read across to 0.007, or 0.07 I should say. And what you will get is 0.9616. You throw that into your calculator. You get 0.768. This is greater than 5%. This is 7.68%, which is larger than 5%. So we are further in. We are inside our 95% confidence interval because our p-value is greater than 5%. So I'm going to write down the English of this and come back to you. So as our p-value is 0.768, which is greater than our 5%, 0.05, that means that we are in this situation here, like what I drew at the beginning. Our area is larger than 5% of our distribution. Therefore, we're inside the 95% confidence interval. Therefore, we accept the null hypothesis. We're inside our 95% confidence interval because we're taking up more than 5% of our distribution with our p-value. The other way of saying that is the result is not significant at the 5% level of significance, i.e. this is an extra bit. You don't need to write this unless they ask you to explain your answer, i.e. there is no reason to believe that the mean of our different light bulbs is different to the population that we already knew. And that is p-values. Again, from our perspective, it's just a little bit of a nuisance that we need to know 2 different ways of testing our sample means. It is a genuinely useful statistical method in reality, but from our perspective, it's just that we need to know 2 ways of calculating the hypothesis test for the sample mean. And that is everything.